Okay, welcome to note set 16b, where we'll summarize the scenario for solving AX equal to B. So we've been developing lots of results and insights into when we have a solution, when we have more than one solution. So we saw how to find the null space vector. The null space matrix. We saw how to find a particular solution. We then found how to fuse those together into a whole slew of solutions, infinitely many. Well, that works when we have multiple solutions, but we could also have just one solution, or we could have no solutions. And the previous note sets have kind of poked and prodded at all this, but haven't really kind of pulled it all together in one grand vision. So this is covering material in section 3.4, and the goal is to try to give you a perspective on how this equation works in all its different settings. And so when you're working with these kinds of things, being able to think through in your head, when this happens, this will be the situation that I'll have. I won't have any solutions, or if this happens, I'll have infinitely many solutions. So, when you're designing a system, well, let me back up. If you're just trying to figure out the answer to something, you don't necessarily need to be able to think through all this. But I've already warned you that just coming up with a numerical answer is not what engineers do. What engineers do is try to think about, how is this going to work? What do I need to do to make it work? So if you're trying to come up with a system that's described by such an equation, AX equal to B, and you want it to always work, you better end up making sure that there is a solution. That would mean, if there is no solution, it would mean that the thing you designed doesn't work. And you also only really want it to work one way, perhaps, the way that you think it should work. You don't want it to work multiple different ways. And so, we don't necessarily want to end up with infinitely many solutions. So being able to think through this from a this is how it works point of view is extremely important for engineering thought. So we're going to look at all the different cases, and there's several different scenarios that arise for solving this. So right now we're going to focus on letting A be a matrix that's m by n, so it does not necessarily have to be square, and has rank r. So those will be the symbols that we'll be throwing about. And it will all boil down to interactions between m, n, and r. And there's a couple different ways that we can peel this onion. And so we'll look at two different ways of kind of formalizing our thinking on this. One is the way that the book does it. And the other is the way that I usually think about it. They both get you to the same place, just in a different path, really. So it's kind of like, I want to go from point A to point B. There might be two routes that can get you there. Both are valid. Maybe both take the same amount of time, but one might allow you to see different sights than the other one. So what do we know before we go off and do much of anything at all about this? We know we've got an m by n matrix, and we know that we've got a rank R. What can we say about R without having said anything else? Well, we know that the rank of R, or the rank R, can be no bigger than the smallest of m and n. So if m is 3 by 4, we know the rank can be no bigger than 3. So that's something we know right away. So let's talk about full column rank and full, that's what we'll talk about in this case, full column rank. So the rank R is equal to n. So what do we know immediately about this? Well, we know that n must be greater than, I'm doing it the wrong way. Let me back this up. We know that n must be less than or equal to m, right? So if the rank r is the smallest of m and n, or can be no bigger than the smallest of m or n, and we know that rank is equal to n, we know that the rank must be less than or equal to m, and therefore n in this case must be less than or equal to m. So if we were to apply our thinking about finding pivots for such a matrix, what we would find out is that all the columns have pivots in this case. That's what it means for the column rank to be full, or equal to the number n. And therefore the number of free variables that we would have would be 0, because the number of free variables that we end up having is r minus n. And remember, n is the number of possible total variables that we have. Actually, it's the other way around. I think n minus r. But either way, in this case, it ends up being equal to 0. What's the null space? Well, for such a matrix, you can find that the null space will only contain the zero vector. So let's think about that for a second. Full column rank equals r. So all of the columns are linearly independent. That's what that's saying. And since all of the columns are linearly independent, the only way we can combine those columns to give us 0, and that's what we are poking at with null space. How do we combine the columns to give us a 0 vector? Well, the only way to combine linearly independent columns, which is what we have here, and get the 0 vector, is to weight them all by 0. So the only thing in the null space is the 0 vector. And so how many solutions would we have? Well, the solution, we could have one solution or no solutions. So what makes the difference? Well, we just said that we have linearly independent columns. We didn't say that they completely span Rm. So our column space here is going to, we've got n columns. Each column is an m dimensional vector, and m could be bigger than n. So we might not actually span all of Rm. Therefore, B could potentially not be in the column space, in which case we'd have 0 solutions. I'm not saying that 0 is the solution. I'm saying the number of solutions would be 0. But if B is in the column space of A, then we have just one unique solution. So that boils down that case. Let's look at an example for this case. So here is 2 columns. We can easily check that they are linearly independent from each other, because since there's 2 of them, the only way they would be linearly dependent is if the second one was a multiple of the first one, and we see that, well, the only multiple would be 1, since that first number has to stay the same, and that won't work for the second pair. So definitely linearly independent columns. So I've got 2 linearly independent columns. So the rank of this matrix is 2. And what we would like to do, so we know that there will only be a solution if B lies in the column space. So whatever this spans. So remember, we're talking about the column spaces in R3, since we have three element columns. But since there's only 2 vectors that span the column space will be a plane. So there will be some restriction on this. So our solution to this, we can form the augmented matrix and do the reduced row echelon form on that. We end up getting our B structure there, and then we can find out what the requirements are. So since R is equal to 2 and n is equal to 2, we have n minus 2 n is equal to 2 in this case, equal to 0, so there are no free variables. And our last equation, if we take this one step further to eliminate this, we'll end up getting this requirement. So that defines a two-dimensional plane in the three-dimensional space, and any b that lies on that plane will give us a solution to this. So here we're showing that a little bit further reduced, and this is the complete reduced row echelon form. We see that we have two pivots. Again, we know that we have full column rank. So there are no special solutions. That means our null space is just the 0 vector. And our particular solution will be the only solution if this B is selected to lie in the column space. If the B is selected so that it lies outside of the column space, then there is no particular solution. So XP will be equal to 2B1 minus B2, and then the second element B2 minus B1. So the complete solution, the only solution, would be this form, and again, this only holds if the B is chosen to lie in the column space. So kind of summarizing this scenario, full column rank, R is equal to N. We know that M must be equal to or bigger than N in this case. All columns of A are pivot columns. We don't have any free variables, therefore there are no special solutions. Therefore the null space is just the 0 vector. And if B is in the column space of A, then there is one unique solution. If it is not, there is no solution. So here's an A matrix. When will it have no solution? Well, whenever B lies outside of the column space. So pick a B that you can't make from a linear combination of those two columns, and you'll have it. But it's a little bit easier to answer when we will have a solution. Well, it will work whenever B lies in the column space of A. And so if we just add the two columns together, we get this particular B, and therefore it would work for that case. All right, let's look at case 2, full row rank. So now the rank is equal to the number of rows. And what do we know about that? We know that this must be less than or equal to n, which is the number of columns. So this would be either a square matrix or a short matrix. The previous case, number 1, could be square or tall. And we'll talk about tall and short matrices as our focus at the end of this set of notes. That's kind of how I like to slice this up. So a tall matrix has more rows than columns. A short matrix has more columns than rows. So here's a short matrix. And if you go back and look at the matrix we were looking at over here, that's a tall matrix. So case number 1 was square or tall. Case number 2 is square or short. So in this case, every row has a pivot. And so how many free variables do we end up having? And what's the rank of this matrix? These are questions that we would like to know. In this case, the number of free variables will be n minus r, but our rank is equal to m, so it's going to be n minus m. And we can find where the pivot columns are. So here's an example for this matrix. We can reduce it to this form. This is the reduced row echelon form, and we can see that we have 2 pivot columns. This is the matrix part, the last thing over to the right outside what I just drew is the D vector that is the transformation of the B vector, the given B vector. So we have two pivot columns, and we have, in this case, one free variable. So the free variable in this case is x3. And so we can find the particular solution. Remember, we set the free variable or free variables in general equal to 0. In this case, since there's just one free variable, we just set that 1 equal to 0. And then solve. So we would put in x3 equal to 0 into this system and solve, and we would find that the two pivot variables are 2 and 1. The special solution, we have just one special solution in this case, since there's just one free variable. So that is just equal to 1. Well, x3 is equal to 1 in that special solution. So if we put that in, we can solve for the two pivot variables, and we would get this special solution vector. So there's just one special solution vector in this case, which tells us that the null space has dimension of 1, which means it's a line. So it'll be a line in this three-dimensional space. So there's what we've got. XP is equal to that 210. Our null space is any multiple of that S vector. And so we can check those. We plug those into with these numbers, and you can verify that those do indeed work. The null space, as I just said, has dimension of 1, since we have just one special solution. And it's the space that is spanned by this vector. So any multiple of S lies in that null space. And our complete solution, well, we just take our particular solution plus all the vectors in the null space. So we just use the free variable x3 as our variable that allows us to span. And a nice picture here, since the null space has one dimension, it's going to be a line. So here's the origin. We're not really showing the set of axes in this three-dimensional space, but you can imagine it's a three-dimensional space. So here's the line. That's the null space. Everything that lies on that line lies in the null space. And then, just like we saw before, we're going to displace that by xp. So there's our xp. In this case, it's 210. So it's a little hard to see why that vector sticking, that looks like it's sticking straight up, is 210, but let's assume that it is. And so this line moves up to that line. And so now any vector that lies on that line is a total solution. So remember, we would imagine taking our xp plus something that was down here, adds to give us this point. So that's really this vector. So it's this vector here that's the solution to that. So that's our visualization for that. And so kind of summarizing this case, if we have a full row rank, that means that R is equal to the number of rows, and we've got all these properties. So all the rows are pivot rows. So when we go to reduced row echelon form, our R matrix has no 0 rows. So that's a key sign. The column space is the entire space. So there is no constraint on B. So there will always be a solution for this case. So the column space is the whole space Rm. And there will be n minus m special solutions. So if n is greater than m, there will be if n is equal to m. So if we have a square matrix in this case, then there will be no special solutions. So what are the other cases that we could cover? We've talked about full column rank. We've talked about full row rank. Well, let's talk about case number 3, full rank and square. So really we kind of already covered that as a special case in each of the two previous cases. This is how the book slices it up, and it does show some interesting things, but to me it's a little confusing because case 3 is actually the shared common case between those two, between case 1 and case 2. So, but let's take a look at it. We've got R is equal to M is equal to N. So full rank, because R is equal to the largest that it can be, and it's a square because M is equal to N. So this is a square matrix. There's an example, simple 2 by 2. If we do our reduced row echelon form command in MATLAB to convert this, or you could do it by hand, you'll find out that it reduces to the identity matrix. And so it's kind of interesting that the identity matrix is kind of a like super special, super good matrix. And it just comes out of this case. And that's what leads to full rank and square being, the nice scenario. And when we're usually solving AX equal to B in some engineering problems where we are insisting there be, the same number of equations as there are unknowns and that there's a unique solution. So like, for example, solving, some set of equations in a circuits problem. In those, we do KVL, KCL, we get multiple equations, loop analysis, mesh analysis, nodal analysis, any of those, we end up getting this case. And that's nice. And it comes about because the circuits have to have a unique solution. You can't say, well, I connected these resistors and sources and I don't know which of the many things will happen. No, this is the real world with circuits. You connect them, they'll always work the same way if they're working properly. So in this case, our null space is the zero vector, and that's easily seen from applying our previous theory here. And AX equal to B is always solvable. Again, that comes from looking at applying our theory that we've seen already to this particular case. So let's summarize how the book views the whole picture. So this is the case we just looked at here, which is full rank with square matrix. We've got full column space, and here we're saying explicitly less than. So that's that. In that case, we're eliminating the possibility of having the square case happen. Then here we have full row rank, and again we're eliminating the possibility of there being a square matrix. So this is really saying, let's see, n is less than m, so there are more rows than columns. So this is short. This is the short matrix case, and this is the. Oh wait, did I have that right? No. Sorry. Got that backwards. Let's see. N is the number of columns, so I have fewer columns than rows. So this is the tall matrix case. I'll just put TA. And this is the short matrix case. I'll just put SH. And because we've not allowed equality here, they are strictly tall and strictly short. And then over here we get a lot of cases that all kind of mix together. In this right-hand case, it could be tall, could be short, could be square, but the important thing is that our rank is less than the maximum it can be. So it's some sort of, I would use the term rank deficient in those cases, or not full rank. And so we capture all of this. So if we've got rank is equal to m is equal to n, so full rank square matrix, we have one solution, very nice scenario. So that's the writing our KVLs, KCLs, getting the same number of equations as there are unknowns, and you get a unique solution because the matrix that results is full rank. Nice. That's how things should work out in a lot of engineering problems. But there are other settings in engineering where we do get these other cases, and you kind of have to know how they all work. What about square where the rank is not equal to m or n? Well, that would be handled over here. M and n would be equal to each other, but rank would be less than m and n. And we'll get to that in a minute. So for the tall case, with full rank, tall with full rank, we have 0 or 1 solution. And then short with full rank, we have infinitely many solutions. And then regardless of tall, short, square, with non-full rank or rank deficient, we've got either 0 or infinitely many solutions. So if you don't have full rank, you're not getting a solution. And look over here. If you're short and you have full rank, you're not getting a unique solution. So the only places you're going to get a solution is either here or here, one unique solution. Now, interestingly, it's this right-hand side that's kind of the most interesting in general, but it's the least common in practice, as I just said. When we're designing circuits and things, we can count on our KVLs and KCLs to end up like that. But in other engineering applications that aren't, held to such strong constraints like KVL and KCL, we may end up with any one of these scenarios. And often what we're trying to do is build our system to make sure that we don't end up, over here, and that if we end up in this one, that we end up with a solution, or even, the best, that we end up over there, well, quote unquote best. But what we see in all of this is that it's the matrix rank that and how it interacts with the actual sizes of the matrix. That's what drives the number of solutions. So you need to be able to puzzle that out. So as I've been alluding to, what we see above is one way to slice it up and think about it, and that's what the book has presented. And I think about it a different way. Totally equivalent, but I'm just slicing differently. And so I'll give you my view on the next several slides. So I like to do these little bifurcation trees or binary trees. So I start off up at the top, and I'm going to say, all I'm saying is I've got a square matrix. I haven't said anything at all about the rank. So I categorize these by I got a square matrix, I got a tall matrix, or I got a short matrix. And the reason that I tend to do that is that these three different shapes of matrices kind of show up in different settings. That, when you enter into this kind of engineering problem, you're likely to get a square matrix, or in this field, you're likely to get a tall matrix, and in this field, you're going to get a short matrix. So that's kind of how I've settled on slicing these things up like this. I didn't see this in a book anywhere. I didn't learn this along the way explicitly like this. It just kind of gelled as I went through and thought about how I use matrices in the work that I do. And as I started trying to teach this stuff, I needed a way to categorize it, and this is what I came up with. So notice that the first binary break is full rank or not full rank. So full rank in this case means that R is equal to N. And there is no M here because we've got N by N. So that's what full rank means. And as we've already established, for that case, square matrix, full rank, our null space consists of only the zero vector. That's the smallest null space that we can have. And our column space consists of the entire space, Rn. So that means any B here will reside in this column space. And since the null space is just the 0 vector, if I try to add that to a particular solution, it doesn't change. So there's only one solution. So I have this case. And why do I not have anything here? Well, this just simply can't happen. As I just said, the column space is the entire Rn. B is in Rn. So any B that I pick is going to be in the column space. So I can't even go down that path. And here's a nice picture that I like to think of. So when we have a square matrix, we can think of, even though we're really thinking of knowing A and knowing B and finding X, I like to think about A mapping X into B. And so if I think about picking X over here, what B's can I get to? And so what this picture is showing us is that any vector X on the left side, there will be some vector X that I can pick that will map into some vector B over here. I can hit every possible B. And so that's what I'm showing here. The column space is the entire space Rn. Now, I've shown these ellipses before, and I warned you that these ellipses and such are just evocative pictures of how these things, of these spaces. They're not precise characterizations. So I'm not saying these spaces are really in the shape of ellipses, okay? The other thing we see is that there is one and only one vector, the 0 vector, in the null space of A. Okay, so that's full rank square. Deficient rank square. So rank is less than n. So I call that up here not full rank. And what we know? Well, we know that the null space contains more than just a 0 vector. So I'm using this symbol here to mean subset or includes. So the null space of A, well, let me say it this way. The 0 vector alone is a strict subset of the null space. So that's just a clever, very efficient shorthand math way of saying the null space has more in it than just the 0 vector. Oh, and what is this saying? It's saying that Rn has more stuff in it than just the column space. So look at the picture down here that we've got. So we've got a null space here that is not just a 0 vector. So everything inside this little kidney-shaped, evocative shape space is the null space. And so everything there will map over to the 0 vector over here. And what about over here? Well, here's the column space. Only the vectors that lie in that little shape are things that I can find an X over here that will map into those. So if I were trying to hit something over here, there is nothing over here that will map to that. Everything that I try ends up inside that little shape that I've drawn there. So that tells us that there are some B's over here. So if I picked this B, it would not be in the column space. So if I go down the path, A is square but not full rank, and my B is not in the column space, no solution. If I go down this path, A is square but not full rank, but B is in the column space, well, then I have infinitely many solutions. Why do I have infinitely many solutions? Let me clear some of this ink off and I'll tell you why. So there will be some X here that will map over to there. But there will be another X that will be that X vector plus something else in this null space. So maybe it will be here. The sum of those two vectors will give me this, and that will also map to there. And in fact, there will be infinitely many of them. And we've seen that. We've seen that the null space might consist of a plane or a hyperplane or a line or something like that. And so there will be infinitely many of them that map in there. So you give me this B, and I can't solve this problem. I can't figure out what X gave rise to it. So this is a condition we want to avoid in engineering problems. So, you're familiar perhaps if you've taken a circuits class with how these equations show up when we write KVL or KCL. But a lot of times these matrices A show up because we're using them to observe characteristics of some system. So like in a radar system, for example, we might be trying to measure position and velocity of a target. Or in a control system, we might be trying to measure our own, velocities and accelerations and positions. And we want to make sure that once we've made those measurements, so that would be, we are given B. That's a measurement that we made by observing some unknown X through A. So we know A, we know B, we're trying to find out what is X. X is a vector that might hold our own aircraft's positions and velocities and accelerations. So, we're talking multidimensional here. X velocity, Y velocity, Z velocity, three-dimensional. And we might even include things like roll and pitch and yaw. So we might have 6 dimensions that we're trying to capture. And so I've got some measurements. So my system that's measuring these things is characterized by a matrix A. I observe the measurements are B, and my goal is to figure out what are the actual things that I care about. Well, if that 1B maps back to several different things, infinitely many different things, I'm not going to know where I am. My airplane? Who knows? How fast am I going? I don't really know. I could be going this fast or that fast. I don't know. So you certainly don't want to design your measuring system with an A that will look like this stuff over here. Bad to do. And so, like I keep trying to tell you, engineering is not about given this equation, solve it for a number or a set of numbers. That's not engineering. Engineering is understanding how these things work so that we can be sure when we build our measuring system, for example, we'll be able to figure out what we want from those measurements. All right. Sorry, got a little heated there. I get excited by this stuff. You should too. All right, next characterization, tall matrices. So you see how I'm not doing it on the basis of interactions between rank first. I do that later. So now let's look at all the tall matrices. And so we've got AX equal to B. And again, the first decision, binary decision is full rank or not full rank. So we've already established that for a tall matrix with full rank, our null space is 0. But our column space is contained inside Rm. And yeah, let's look at the picture. So here's our null space, just this. So we know that if we have a solution, it will be unique. But our column space sits over here. It's inside, strictly inside R sub m. That's our column space. And so what if our B was out here? Then there is no vector over here that will map to that. Nope, can't do it. Only if I pick a B here can I find an X over here that maps to it. And once I find that X, it will be unique. So that's this dichotomy. Maybe I should say bichotomy. Between B in the column space or B not in the column space. So we get no solution or one solution. Now, when A is not full rank, same kind of thing. Let's focus on this part first. Column space is still strictly inside Rm. So regardless of whether we're full rank or not full rank, we've got no solution if B lies outside of the column space. So we could actually redraw this with the first decision based upon B in or out of the column space. Then ask the question about full rank or not full rank. So you should, it might be interesting for you to try to redo these where the first question you ask is full rank or not full rank. And then ask, I'm sorry, that's the question I asked. in the column space or out of the column space, and then ask the question, full rank or not full rank, and you'll be able to see a different slicing of this, and that actually matches a little closer to what the book did. So all the things that I just said before about designing a measurement system or something like that, we might be taking more measurements, M, than the things that we're actually trying to observe. So, we might be trying to observe XYZ velocity, XYZ position, XYZ acceleration. So there's nine parameters, but we might take, 20 measurements in order to do that. Those measurements might be redundant, and we're doing that maybe to help combat noise in our system, or to help combat to build in some redundancy. So if one of the sensors fails, our aircraft won't crash because we can no longer measure a certain position. So this can show up in that same scenario, but where do you want to be? Well, you'd like to be in the one solution case. Okay, so you certainly don't want either of those. You don't want there to be no solution. And you would prefer to be over here, full rank with B in the column space. So if you're designing your system, you better figure out how to make it show up there. So you've been tasked, design a measurement system that will consist of measuring X through the matrix A. You don't know what X is, but you have a way of measuring it with the matrix A and observing B. Now you know B, you know A, find X, the thing that you really want to know. You better be over here. You better make sure you're right there. So you get to choose, you get to design the A to do that. All right, last slide. Now we've got a short matrix, and now we've got, again, full rank versus not full rank is our first binary question. So if we go full rank, A is full rank, but because it's a short matrix, we now have that the null space is bigger than just the zero vector, but we know also that the column space of A is the entire RM. So if we draw our little ellipse pictures down here, we've got the column space over here is this entire RM. So there is no B that I can pick that won't lie in the column space when I have full rank. So this path cannot happen. So as soon as I know I've got short matrix with full rank, I'm right there. But look at my null space. My null space is not just the zero vector. I've got a kidney-shaped null space. It's not really kidney-shaped. Remember, these ellipses and kidneys are evocative, not precise and characterizing. Okay, but I've got infinitely many vectors inside that little kidney that when I add to whatever the real X is will give me some other X. So that would be bad. So you don't really want to end up over here. But notice that this short matrix case is horrible. You don't really want to end up with short matrix if you're designing a system, unless you can be very, very clever. So if we end up over here with not full rank, well, we could end up with no solution or infinitely many solutions. Now, I will just briefly mention, I'm not going to dwell on this. Oh, yeah, I should show you the picture. There we've got two kidneys, one for the null space, one for the column space, although that's kind of a weird looking kidney. It's a kidney with a little extra knee growth there or something. But there is a new field in electrical engineering and computer science and other related areas that are actually taking advantage of the short matrix view. And so theoretically, in the most general setting, there's no way to figure out a unique solution. But if we know that there are certain constraints about X that we know will be true, so maybe X, we know that X is a 100-element vector. So we're in our space that is over here, Rn, so n is 100 maybe. But maybe we know that 98 out of those 100 elements will be 0. We just don't know which ones. So there's really only 2 variables that are non-zero. We don't know which ones and we don't know what they are. But the cool thing is that people are now figuring out how to deal with that problem, and it's leading to some very interesting engineering developments. And that area is called compressive sensing, or sometimes called compressed sensing. And if there's time, I'll do a video or two at the end of the course if there's time. Even if we don't have time to have it done during the regular part of the semester, I'll try to get them up so that if you're interested in this kind of stuff, you can watch them. And I think that's it. Yep, that's it for this set of notes. And hopefully you can sense the excitement I have about this. This is where things start to become really interesting. If you can learn to navigate yourself through this kind of thinking, you're well on your way to being a good engineer who can apply these kinds of things to come up with interesting stuff. Like, for example, compressive sensing. For a long, long, long time, people looked at this scenario and said, it's hopeless, it's hopeless, it's hopeless. And then somebody came along and said, well, you know what? Infinitely many solutions, but I'm clever. Maybe I can put some additional constraints. And maybe you'll be one of those people who will take these ideas and put them to work in a new creative way. All right, we'll see you in the next video.